I'm Tali Dekel, and the name of this course is Deep Learning for Computer Vision Fundamentals and Applications. And this is, I believe, the fourth time this course is given. And each time, I guess, each year we are saying that we're not going to change anything in this course, but each year the field is rushing through so quickly, so we will keep updating the materials every year. You can find some online recording from, I think, the first time we gave it, but this time, given the situations, we're going to record everything. So all the most up-to-date classes and tutorials are going to be available to you. I was lucky enough to co-teach this course with this amazing staff, which include a lineup of lecturers and TAs that are going to be available for you. Some of them are on reserve these days, but we do have part of the team here and available. So I think Assaf is going to talk more about the logistics a bit later. So I'm going to just jump in. So this is just an introduction, and wanted to tell you a bit about myself. Just a very brief overview of my career path. So I did my degrees in electrical engineering at Tel Aviv University. My PhD there with Professor Shai Avidan. I don't know if you know him, one of the founders of, I forgot the name. What? Not Briefcam. Oh, Mobileye, yes. And the son of Amnon Shashua. And then I moved to Boston for 6 years, where I did a postdoc at MIT with Professor Bill Freeman. And then Bill opened the research group at Google, which was just across the street from MIT. So I joined him in Google. So overall, I spent 6 years in Boston, and then decided to return to Israel and join the Weizmann Institute 3 years ago. And that's where we started this course. And I have a research group here at Weizmann, which includes about 8 students at this point. And I don't think this is a representative photo. Most of the time we are here at the lab, and sometimes we are trying to have some fun. And we're working at the intersection of computer vision, computer graphics, and machine learning. And this field of computer vision has gone through some really major revolutions in the past decade or so. And when I did my PhD, there was only very partial overlap between computer vision and what's called deep learning or machine learning. And I'm sure that, as you know, today, this is the situation. I think starting with the revolution of the deep learning, which took over our field somewhere starting around 2015. So now I think, 99.9% of all the methods or algorithms or frameworks that we have in computer vision are based on deep learning. It took me a while to, enter this field of deep learning. I used to work with classical computer visions and build algorithms that we understood line by line what they are doing. So it took me time, and I think around 2015, 16, I was still giving talks using this slide that, warning, no deep learning, the entire world is going through this revolution, and I'm still kind of like left behind. But while, I guess nobody could ignore this revolution, and it really enabled some really tremendous progress in the field. And since this revolution has happened, we are really in the midst of another revolution, which is the a generative AI revolution. And I'm sure you guys are all aware or know that we are now able to, synthesize these amazing, mind-blowing images just using, for example, text. So we really reached some major breakthroughs in generative AI, in our ability to synthesize visual content. And more generally, we are seeing this paradigm shift in the field where we are moving from task-specific models. For example, a model that was trained specifically to recognize objects in images. We're moving from this paradigm to what is called foundation models, which are huge billion parameters models that are trained on a massive amount of data. So for example, all the images on the web. And these models, they are so powerful that they can learn this universal representation of our visual world, which we can then use for many different tasks. So this is really an exciting time to enter this field, because it feels that everything is possible, and we have such powerful models of the visual world that can open up so many things. So just to give you an example, these are synthesized images using this text, the first class in computer vision and deep learning course taught at Weizmann Institute. And I think it's amazing how, how it resembles this Ziskin 1 classroom. Yeah, so I just want, I won't take much of time today. I just wanted to give you very brief, few quick advices on how to enter this field. And especially because we are in the middle of this revolution. So the first thing I want to suggest is that you strive to still, learn the fundamentals. And what I mean by the fundamentals, I mean strive to have a good fundamental basis in signal processing and in computer graphics and classical computer vision and mathematics. I think there is the Introduction to Computer Vision course that is given also in parallel to this course. It's a complementary course to this one, because we are much more aiming towards, applied deep learning for computer vision. The introduction course is really going to give you a good basis of classical computer vision that is going to benefit you in all research stages if you're going to enter this field. I really believe that, learning concepts behind classical methods is very valuable, and it allows us to really build some more sophisticated and grounded deep learning based frameworks once we understand those fundamentals, because we can integrate those concepts and these ideas to modern deep learning based design. The second thing that I want to suggest is that you will always strive to understand the model that you are building, training, testing. It's really easy to just, think it's doing what you want, but most cases it won't. And I think it's very important to be critical and always ask yourself, what does this model learn? Convince yourself, always be suspicious of your model. Is it cheating? Is it doing what you think it's doing in all these end cases or toy examples? Or anyway, don't believe this model. I know this is going to be very, I know it's very up in the air, but you will, during this course, you will experience with hands-on design, training, and of deep based models. And in the end, you have a function that is huge, could have millions of parameters, and debugging it could be difficult, but I think it's very crucial to ask those questions, understand the limitations, understand the end cases, understand to which extent it works. It will allow you to build better models. So as I said, the field is rushing very quickly. We see every day new technologies that are coming out. It's really hard to even keep up with what's going on in the field. But I think you have to understand that this is not a sprint, it's a marathon, and you are now starting your marathon. And it's really important to live, to sometimes leave your energy, to the miles to come, and build a good fundamental basis. And this requires sometimes slowing down. even if it's very tempting because all the source code and everything is available. It's very easy to just plug and play boxes. I really think it's important to sometimes slow down, take the time to understand what you're doing in order to then speed up. Fourth advice is that luckily we are dealing with images, with visual data. So it's not something abstract. It's not some subspace in a parallel universe. These are pixels. And what's great about them, that you can visualize them, you can inspect them, you can look at them. And that's what I encourage you to do. When you design and train models, it's always beneficial to go back to the data, visualize the data, visualize the images, visualize the visual words. Don't just count on curves or just numbers of some functions that go down. Always look at the data. And lastly, I just want to say that we have part of this course is going to be based on a project, a personal project that you will be able to come up with the idea for this project, everything, the idea, implementation, and carry it on to its success. And just wanted to say that I want to encourage you to start thinking about this project from today, and dream big. We are seeing so much, again, great advancements in this field. And I think, you should allow yourself to dream a bit and think about cool projects that you want to do during this course. We are seeing great advancements in, our ability to render the world, view it from different angles in 3D. We see many applications related to autonomous driving. Of course, the level of face recognition and object recognition has been, dramatically getting better and better. And we are seeing, again, as I mentioned, the revolution in everything that has to do with creating content, in generating new content, interacting with the visual world, interacting with images and with videos, and modifying them and perceiving the world in a different way. So yeah, I guess that's my takeaway messages for this class and for you. And again, welcome. And I'm gonna hand it off to Assaf. And I'm sorry for my voice again.
My name is Assaf. Okay, I'm a postdoc at UC Berkeley. My family and I recently returned to Israel. I'm also a visiting researcher in Google. And I'm going to quickly go through a few of the details, I would say, and introduction to our course. Then we'll get into things. We'll just quickly say that everything you need is on our website and the Moodle. So these are the two modalities. So it's very simple. It's DL4CV, the Deep Learning for Computer Vision at GitHub.io. And the course is 4 credit points, and we're going to have these meetings twice a week, and it's going to be 2 hours each time. Sometimes tutorials might be shorter, but tutorials do cover new material. So it's not like rehearsing or solving things. It's actually new material. And the communication is going to be through Moodle, so you can send messages there and ask questions if needed. We are going to have 3 homework assignments and the final project eventually. And the one point to make about this, these are demanding. So you should be aware of this and have your schedule available for it. Some of these require both coding and working hard, so be aware of that. And with that said, everything related to reserve duty or any other effects of the ongoing situation now in Israel, we support everything, every problem, any problem you encounter with, come talk to us. We will help with everything. No one should be in any way hurt because of things related to at least as far as we have to do with it. No one should be hurt because of the ongoing situation now in Israel. So when we built this course, it was actually 4 years ago. We didn't do this. We didn't just build it from scratch. So as Newton said, that if we've seen farther, it is by standing on the shoulders of giants. This course was built using these other resources like the famous deep learning book and the famous course from Stanford. But it's not like we're doing the Israeli version of those. So what we're doing is going to be different. And here are some of the principles that we build this course upon. So one thing is we're going from the most basic to the most state of the art. So we need to navigate here between two extremes. So it's very, very important to go to the most fundamental things to actually understand what deep learning is and all the basic stuff. But it's also super important to go to the most recent advancements, and so that we're all updated and we're doing the things that people are doing today in the field. The next thing is that it's going to be slightly biased towards the research done here in Weizmann, through the understanding that most of the people in this class are going to do their PhDs or masters together with professors here in the Weizmann Institute. And we're going to talk about a lot about intuition, sort of understanding why things are working or several aspects to look at things. And it's going to be hands-on. We're going to be coding, and we're going to talk about code and details, and it's not going to be like philosophical. And one of the most important things is the openness. We're teaching eye level. Feel free to approach anyone. Feel free to ask any question. Feel free to tell us that we're wrong. We're wrong in many of the times. So we're all like, we want this relationship to be constructive. Here's like a few ways to see that you're in the right place. So the prerequisites for this course are not very demanding. So this is what we assume that you do. So we assume you know basic calculus. So you should know, for example, what a gradient is, and basic algebra. So you should know basic like vector spaces, matrix stuff, eigencomposition. And we do assume that you have written some code before. You don't have to be like a master programmer, because this is like in programming sentences, it's not like a huge software engineering, but you should be comfortable with solving things using computer code, preferably Python. But if you did other things, Python is easier than anything else. And we do assume that you bumped into some of like that buzzwords, that you know basically like what machine learning is in general and some terms people sometimes use. If you don't, some of this can be mediated, but this is sort of the starting point for this course. I'll say a few quick things about homework. So we have this philosophy for how we construct the course homework. So it's divided to 3 parts. So every assignment you're going to get has these 3 parts. So the first part is going to be theory. So you'll get one question which is theoretical, trying to solve something that is mathematical and related to what we're doing. The second part is, we call it from scratch. So you're going to be coding one of the basic principles that we learned, and you're not going to be using like the ready-made functions in the frameworks to do it. So this is things like writing code for a neural network from scratch, things like this. And then there is the applied part, which is important for you to be relevant to actually work on like mini projects using the existing platforms and solving challenges using this. And the first homework is already online, so check it out in the website. There's also the due date and everything there. And you're going to be ready to do some of this today, and then after this week's tutorial, you'll have what you need to do the entire thing. This is a slide I borrowed from Justin Johnson when he was at Stanford, and so to understand where we are, where this course is. So in the world of AI, there is this world called machine learning, and it has some intersection with computer vision. And in machine learning, there is this method or bunch of methods referred to as deep learning. that has also a big overlap with computer vision. And this is exactly where we stand. So this course is about this overlap in the middle there. And for today, what we're going to do, we're going to quickly talk about some motivation and the history. We already sort of started this part. Then we'll learn what supervised learning means, and then about specific method called linear regression, then an optimization method called gradient descent, and we'll end up with feature transform, which will be the starting point for our next class next week. So just about deep learning. So things have been really impressive through the years. So this is almost a decade ago. We could recognize images and specify in text what's in there. And also almost a decade ago, we could do this in real time and for object detection. And Tali showed you some impressive examples, and people were very optimistic about the fact that AI is going to change the world and is going to do major things and change the way we think and improve life. So, but this is for good, impressive people. And people like me, what I care about is doing stupid jokes with AI. So this is me on ChatGPT trying to generate my stupid joke, saying, generate a picture depicting the joke, a snail on the back of a turtle saying, woohoo. And this is what I got at the first time. But the reason I'm showing this is what's nice in this new Dali 3 with OpenAI is the interaction. So I wasn't very happy about this because it doesn't look like really like the snail is woohooing. So I complained a little bit down there, and I said that that's very good, but I want to look like the snail actually feels the speed. And we were able together, ChatGPT and me, to improve this picture and get my stupid joke going. So there you go. AI is changing our lives. Okay. We're going to cover the history very quickly of what that ends about when you're like the end point of this is you sitting in this class. But what brought you here is this common history of these two fields of computer vision and machine learning, and it was affected by computer science, mathematics, and neuroscience through the years. And it actually starts very early on. So 1943, there was this these dudes, McCulloch and Pitts, and they were the first to suggest this mathematical model of a neuron. It wasn't a learnable neuron, but it was this very basic mathematical model, and it was supposed to depict elements inside animals' brains. And then in 1957, there was the first algorithm proposed by Rosenblatt. It's called the perceptron. And this is sort of a linear neuron, single layer. And it actually had an effect, and it was an important algorithm at the time. And this is the let's say the grandfather of the deep nets that we're going to learn about soon. Then in the world of neuroscience happened a major thing where Hubel and Weisel did this famous experiment. So there was this cat, and they were showing in these lines in different orientations, and they found out, and they had like electrodes in his brain. It wasn't very humane, and then they found out that he had those specific neurons firing whenever the cat was shown to has seen specific orientation. So it was kind of like specific orientations had specific neurons, and this was somewhat of a revolution that started an era of neuroscience trying to figure out how these neurons work and what this firing means, and how things actually work in animal brains, and it had effects on also on the algorithmic world. But then happened this thing. So Marvin Minsky wrote. He was a famous professor, and he wrote this book. And in his book there was an example called the XOR example, and it was shown that the XOR example, like classification of XOR pattern, cannot be solved by this thing called the perceptron, and this was kind of a very bad, had very bad reactions. People stopped believing in this perceptron, and consequently in AI in general. And this sort of started, not only this, there are like many other geopolitical reasons, but it started an era called the AI winter. But we're going a step back when nobody cared about anything related to AI. In the beginning of this AI winter, there was this student, this was the first PhD graduate of computer science in Finland, and his name is Janima, and he came up with this weird algorithm called backpropagation of how to calculate derivatives of structured layers of matrices. And nobody cared that much about it at the time, but this is going to play an incredibly major role in the future. Also in 1979, there came out the famous book by David Marr. He is like the godfather of computer vision from MIT, and this was trying to explain human vision and the structure of how we see and interpret things. We also have our Israeli contribution there. So for today's Professor Shimon Ullman was writing the preface for this book. He was a postdoc, and in 1980, Fukushima comes up with a thing named neocognitron, and this is the first father of what today we call CNN, convolutional neural network, and this is already in 1980. And in 1986, Jeff Hinton comes up with using this backpropagation from 1970 in these structured neural networks, layers of matrix multiplications, and as a way to optimize them. Then there is another era, they call it the second AI winter, when companies and governments didn't want to invest in AI anymore. But during this time, this guy is called Jan LeCun, was in Bell Labs at the time, and he was showing this thing he called convolutional neural networks. And he used this backpropagation from 1986. He used to be a postdoc with Jeffrey Hinton, and he's showing this thing from this backpropagation using this Fukushima neocognitron combined together to this CNN, and is able to recognize digits, which is very impressive in 1989. But actually, nobody cared too much about neural networks at this time. So a few important things happened that you might learn in other courses about. So the kernel SVM by Vapnik and Cortez arrived at 1995, and everyone was excited about it, and they used this for AI. In 1998, there was the improved Linnet by LeCun, this guy Jan LeCun, CNN, but people didn't care about it too much, because also in 1999 there was this SIFT you might learn about in the classical vision course if you take it, and people could use it to do 3D reconstructions, and they were crazily happy about it. And then the random forest came at 2001, and Viola and Jones came up with the first very good face recognition method using AdaBoost. So this whole era, it cannot be called an AI winter. It's not an AI winter, but it is somewhat of a neural winter, because nobody cared about neural networks. Nobody wanted to study them, and those people pioneering them, some people I mentioned like Jeff Hinton and Jan LeCun, they were PIs, and they couldn't get students to work for them. But things have changed at once, and the year was 2012, and in Jeff Hinton's lab, Alex Strichevsky built this neural network, this CNN, and he used, instead of using the computer's CPU, it was using the GPU. He wasn't the first to do this, but he was the first to do this very successfully. And this method was used for image classification, and it got results way better for any other competitor that was previously. And people started going crazy. One of the authors there, Ilya Sutskever, is today one of the leaders in OpenAI. And this started a huge revolution, which eventually brought you guys to this classroom. On the way, we have these generative adversarial networks and some impressive architectures that had big effects later, including also the transformer, but Ashish Vaswani. And a nice point to end this history part is 2018. So these three guys, Yoshua Bengio and Jeff Hinton and Jan LeCun, they got the Turing Award. And this is after many years their contributions were not recognized, and nobody cared about deep learning. They finally got their recognition. And I should mention that a lot of history is still going on since then. So in this last 5 years, Tali mentioned the generative AI revolution, the large language models, the foundation models, and all these huge things that are now changing our lives. So that's it for history. And we're going to discuss now supervised learning. So, yep.
Are there lecture notes somewhere?
So this can be available, like the slides.
Yeah.
Yes, this is available on the website. Will be uploaded.
Not there.
Okay. Okay. So So now we're getting into the material. So supervised learning is this paradigm, I'd say, and it depicts a really basic challenge. So it's best explained by example, and one of the most famous examples is email classification. So you guys are getting email, and you have your spam box. So you're getting emails that are either spam or not, and sometimes non-spam emails are sometimes referred to as ham. This is because this term was coined in the US Army, spam and ham. And you have you have this list of emails that you got. And the challenge now is, if I have some examples, if I show you some examples and their solution, and I show you many of them, I want the program to be able at some point to do it by itself, to be able to classify just using those examples. This is a paradigm. We're now talking generally in machine learning. This is a paradigm very different from rule-based AI that people used for many years. So I'm not trying to figure out a set of rules of how to determine whether an email is spam or not. I'm not doing this. I'm assuming that it's complicated and that I don't know how to provide this set of rules. And I'm looking for an algorithm to learn this set of rules. And I may or may not know these rules eventually, but this algorithm will be able to use those. And it's going to be based upon examples. So specifically here, you can see we have these rows. Every row is an email that I got. Okay, and every such email has these properties. I call every such email, I call these these are instances, and every such email has these features. So for example, the number of new recipients or the email length. Okay, these are some features that each email has. And then I have what we call labels, and the label is kind of the solution. Is it spam or is it not spam? Okay, and this is my data set. I have these examples. I want to use this data set so that when I get a future email, the system will automatically be able to tell whether or not this is spam. So for this example, we're only going to use these numeric features. So I'm going to kill the other ones. And when I do this numerically, I can look at this space. So in this particular case, I have 2 dimensions, the number of new recipients and the email length. Okay, so these are 2 dimensions, and every instance can be looked at as this point in space or as a vector in space. Okay, and when I put them in space, now it can be, you can use your own eyes, but what if I had a million of these dimensions? Okay, and I'm using, this is what we call binary classification. There are two classes, either spam or not, and I'm using a color coding in this case to show you whether or not it's spam. And I want to come up with this rule so that my system has this rule that for the next time it knows what to do. And this rule can look something like this. I draw this line and I'm saying, okay, everything on this side of the line is spam. Probably, maybe, I don't know, according to my data set. And everything on this side is not spam anymore. And then when I get a new example, say I get, this is a new email that I get, I place it here. So I think can you tell me, is it spam or not? Anyone? Red means spam, blue means not spam. So it's spam, right? Probably is the best answer, actually, yeah. Probably it's spam because it's on this side, so I can classify it. And this line, this rule that I have, and the rule that you looked at and helped me to classify this, we call this hypothesis. Okay, this is the hypothesis, and the hypothesis is actually the result of the learning process. This is what I want to come up with. This is my product. Okay, if I'm going to sell some product to people, it's going to be this hypothesis. Okay. And the act of being able to predict something for an example that I haven't seen before, for a new example, this is a very important part of supervised learning, and this is called generalization. Okay, this is my ability to provide predictions to things that I have not seen before. And here are some examples for types of supervised learning challenges. So one is named regression. And this is when you want to predict a number or a vector or anything that is continuous. Okay. And there is classification, which is the discrete type of challenge. So for classification, there would be classes that I would want to say for each instance which class it belongs. So we talked about a binary classification example, but it can be multiple classes, thousands of classes. So just as an example, so for regression, you can think of image in computer vision, you can think of image denoising. So I get a noisy image and I want to generate a new image that is noise free. So you can think of this image as this list of pixels, like a very big vector of whatever 256 by 256 that I want to predict using another noisy vector. Or localization, for example. I want to predict coordinates of this bounding box of where a sign is. And in classification, I think it's very clear. So this is just a silly example of classification between dogs and cats. Okay. So these are the types of problems you would bump into usually, classification and regression. Yeah.
The distinction between regression and classification is just relies on what the result of interest is to us, or is the process also different? In both you're basically aligned.
Forget about the line. It's not going to be a line. Just in this example. So not exactly, because you look at this and you think about this curve, but it's not about this curve. It's about the rule. The rule can be very complicated and saying. It can be very discrete, saying if it has a mustache and it doesn't have a beard, and if so and if that, then it belongs to one class and not the other one. And it's going to be discrete. So you can only, in the end of it, you will only be able to provide one class. You're going to say this belongs to that class. Whereas in regression, you're going to have to predict like a number of vectors out of this continuum. So the challenge is different. Sometimes the backbone can be similar. You can use like similar layers of neural network, but the ending of it has to be different. Okay, let's dig into it and really understand supervised learning. So the process is built this way. we're going to have a training set. This is our data set. This is the most important thing that we have. This is going to go into a learning algorithm. This is what we're doing. We want to have a learning algorithm. And the outcome of the learning algorithm is going to be H, a hypothesis. This hypothesis can later be used to be applied to unseen data and to provide us with some predicted labels. So we use X and Y to term inputs or instances and labels. And look at this equation here, A of S equals H. So S would be the training set, A is the learning algorithm, and H is the hypothesis. But let's dig into those things now. So the training set, let's look at how it's going to be built. So it's going to contain this big matrix X and this big matrix Y. And in X, just as we've seen before with those emails, so every row in this matrix X is an instance, and each instance is a vector, and the terms in this vector are the features. So for example, this can be like X2 can be some email, and it's going to have, I don't know, maybe 5 features. And if I have 100 emails and 5 features, this is going to be 100 by 5 matrix. Are we good? Great. Then we have the labels. The labels can be scalars, but they can also be vectors. So it can be a matrix, or this can turn out to be like just a matrix, like just like this long vector. So for every email, for every instance, we have the label. So it can be spam or non-spam, and then it's like a binary thing. But it can also be, for example, that this would be like a noisy image, and this would be a clean image. Then the length of each vector here is going to be the same as the length of each vector there. Okay. So remember this structure, because we're going to be building upon this. So we have the matrix X and the labels Y. And it's not just, the matrix is not just a list of vectors. We're going to use matrix multiplications with those things. So it's intentionally put on this way. Okay. Now, we're here mainly to discuss the learning algorithm, which we term here A. And I want you to remember this. Every supervised learning algorithm has these 3 elements. It's built out of 3 things. So one thing is the hypothesis class. The hypothesis class suggests what are the possible hypotheses that we are able to use. This can be finite. So for example, I can come up with not a very good learning algorithm saying I have only 3 possible rules. So think about those lines with the emails. It can only be this line, that line, or whatever, something that looks like a cosine. Okay, these are the 3 rules. This is a valid hypothesis class. Usually, though, the hypothesis class will be infinite. So an example for an infinite hypothesis class: all linear functions. Okay, all polynomials. Okay, things like this. Okay, and then it will be infinite, and then we assume that every such hypothesis it's built this way, so it goes from the world of X's to the world of Y's. The next thing every supervised learning algorithm has is a loss function. The loss is sort of the metric, the way we evaluate. So the way we know how good we are and the thing that we want to optimize. For example, if I'm trying to denoise an image, I have a noisy image, I want to predict a clean image, and I predict something. I need some number saying how good I am, how clean is that image. So one thing I can do is I take the predicted clean image and I take the ground truth real image, and I subtract them, and I take the mean squared error, the square of this subtraction, and sum it all over the image, and this is sort of the loss that I have. So if it's 0, then I'm doing perfectly good. If it's big, then things are bad. And lastly is the optimization method. And the optimization method is using those other two parts. And this is what supervised learning is all about. So it's about using an optimization method to search for the hypothesis in the hypothesis class such that the loss is as small as possible. This is what we're doing here. That's all. I'm sorry if it's not as sexy as machine learning first sounds, but this is all we're doing. We're using an optimization method to find the hypothesis in the hypothesis class that reduces the loss to be the minimum possible. Okay. And so this is in general. This is supervised learning in general, and now we'll discuss one type of challenge in supervised learning, and this is called linear regression. And as you may understand, we already understand both parts of the name. So it's going to be linear, and out of classification or regression, we're going to be talking about regression. So because I'm introducing now a supervised learning algorithm, this means that I have to provide you with three things, the three elements that I mentioned. So if I want to introduce this, I need to explain to you first which hypothesis class we're using. So the hypothesis class we're going to be using now is the linear hypothesis class. And this hypothesis class is as follows. So I'm going to have this, all the h's are going to be such that there is a set of parameters, theta. So there are going to be n plus 1 of these thetas. And the hypothesis class is going to be all the functions that can be written as you see here. So I get this theta 0 plus multiplying each element of the vector with some theta. So the vector has, so I have these n features in the vector, and I have n plus 1 parameters, and this is just multiplying all of them and adding a bias. So if it was just in 2 dimensions, sorry, if it was just in 1 dimension, then I have 2 parameters, and this would be looking like this. Okay, like a line. But if it has more, then you can imagine how it looks like. And there is a nice a vectoric way of looking at it. So it can be, it's just like theta 0 plus this theta transpose multiplied by x. So the tilde is to say that it's without the 0, without the theta 0 in there. Okay, but it's going to be easier if we do this nice trick. So instead of adding this theta 0 all the time, so we can say I'm just multiplying theta. This is just a dot product between theta and the vector and an input vector, but I'm going to add this 1 at the beginning. And you can calculate this and see that whenever you do this, it's like adding the theta 0 before. Okay, so basically this is the linear hypothesis class, just multiplying our vector by a vector of parameters, okay, by n plus 1 parameters. The second thing I have to tell you when I introduce a new algorithm is the loss. So we're going to use the very classical MSE, mean squared error, okay? So basically what we have the predicted, we have the label, we subtract one from another, and then we take the squared norm of it. So I have here h of x, xi is some instance, h theta is some hypothesis from our hypothesis class. I subtract yi, the matching label. I take the square and I sum it all over all dimensions. Okay, this 1/2m is just for convenience later. M is the number of examples that I have in my data set. So I run over all the instances in my data set, and this is the loss. Okay. And so and if you want to look in the matrix way, this is equivalent to taking the entire matrix of X, so all the instances that I have, and multiply it by the vector theta, and then I subtract all this huge matrix Y, and then I take this this norm of the subtraction. You can make sure later that it is exactly equivalent, because here I just sum it all over the instances, so I might as well take the entire huge matrix. Okay. Next is the optimization method. So this is the loss, this is the hypothesis class. Now I need to come up with a way. How do I find the best linear mapping that will make this loss as low as possible? This line here, is it optimal, is the best? And for this, we're going to have two methods that we will discuss after a short break. So let's have a really short break, 10 minutes, okay? And please don't be late, okay? So that we can make it all in time. So we'll continue. Okay, so before we went out on the break, so we're talking about linear regression, and we just mentioned that I gave you the hypothesis class and the loss, and then we mentioned that for the optimization method, we're going to have two alternatives at this point. One is called normal equations, and the other is gradient descent, which is going to be very important for you for the rest of your life. And so I want to start by discussing normal equations. This is a very basic thing in solving linear problems. So basically what we're looking for is this set of parameters, this vector theta, that minimizes the mean squared error, this y minus x theta. Okay, x is a matrix. Y, for this sake, now is going to be a vector. So it's like we're assuming all the labels are scalars. So since we have many instances, it's going to be an m long vector. So this is what we want to minimize, and we're going to do this by a mathematical intuition, I would say. So think about this vector as the vector y that we want to minimize. So we want x theta to be as close as possible to it, but here is the problem. Since x theta is a matrix multiplying this vector theta, whatever we come up with is going to be on the span of the vectors of the matrix X. Okay? So we're stuck in this subspace, whatever we do. Okay? And now we're looking for the best X theta, and we're going to use a geometric intuition here. So I would say this. Whatever I come up with, I can look at the difference. I call this the error vector. So the error vector is just this predicted minus ground truth. So it's x theta predicted minus y. And my question to you is, can you come up with some characteristic to tell me about this error vector, so that if it stands, we know we've done the best that we can do? Any idea? Think geometrically. Exactly right. So we want the error vector to be perpendicular to this subspace, right? Because this is the shortest distance that we can come up with. There is nothing shorter that we can have. So let's just formalize this, okay? We have this error vector, and we want it to be exactly perpendicular to the subspace, and which means so this is in geometrical language, but in algebraic language, it means it has to be orthogonal, right? So it needs to be orthogonal to every vector in X, and in particular to every row in the matrix X, right? So in order to do this, we just formalize this. So we say, we take the matrix X and we take this sort of dot product with the arrow vector. So this will be, this is a set of equations, right? For every row in this matrix, and it needs to be 0 because orthogonality means dot product or inner product is 0. Are we all good? Everybody's with me on this? Okay, great. And now we're going to just jiggle around, and we're going to, you know, we'll open these brackets, we'll multiply, take this to the side, multiply by the inverse of this matrix, and then we get to this point, and this is called the normal equations. Okay, so the predicted theta is going to be this formula. Okay, X transpose X. We take the inverse of it if it exists. If it's not, it's a different discussion. Multiplied by X transpose again, and then Y. This is the best you can do. Okay, so there is no too much of hard work. This is just a closed form. This will bring you to the absolute best. Okay. In your homework, you're going to prove this formally. Okay, and then you'll know it much better, and you'll also be discussing this invertibility of X transpose X and what it actually means. I'll just mention that if it's not invertible, if it's a singular matrix, there are other things you can do, and you can read about the Penrose Moore pseudo inverse. Okay, so maybe some of you are already so, and this is like a special case of it. Okay, but is this really practical? Sometimes it is. In many cases it is, but in many other cases no. And there are two reasons. So one reason is that inverting. So you saw this X transpose X inverse. Inverting this matrix can be very demanding. Think about this. This is the matrix of all the data we have. This can be, I don't know, think about emails, think about images. It can be like millions, billions. Okay. So now you want to take this, look at it as a matrix, and I can't even fit it in my memory. Okay. And the other thing is that this is very, very special to this special case with this special loss and these linear things. But you probably understand that we're constructing things to get more advanced. So if we have a different loss, if we have regularization, and if we have things that are nonlinear, this is meaningless. You cannot use these closed form anymore. So this brings us to our next alternative, but I won't say it's very important. It's like super important thing in like solving linear problems that you should really be aware of. Okay, but this brings us to gradient descent. So the idea of gradient descent is taking small steps down, okay, step by step. And this is me many years ago, and it's in India, presumably close to the highest village in the world, allegedly, not exactly. And I did this thing, this hike of starting there and then going down all the time. I didn't have any map or anything. So the only strategy you can have in such a situation is say, I'm just going to walk down. Whatever happens, wherever I am, I'm just going to aim myself to go down as farther as I can. So if this was me here, I would start there, and then I take another step, another, going all the way. And this way I'll be getting down. Okay, can we guarantee that I will get to the global minimum?
No.
No, and actually I wouldn't, right? Because the global minimum is the Dead Sea here in Israel, right? And there is no real path going there. So what can I guarantee? Local minimum, exactly. So we will have to assume, and it's a very good assumption if you read theory stuff, that you're not going to meet any volcanoes or craters. Okay, these things where you go down and you at a high point, but you're kind of stuck in the local minimum. We're going to have to assume this. Okay, and you can look at how gradient descent would look like when we look at two different things. So you have the data space and you have the parameter space. So in the data space, these are 1D data points, and we gradually improve the hypothesis that we select. So we improve the parameters, and this is the parameter space. So you see, this is theta 0 and theta sub 1. Okay, and this is the loss. But all the data is frozen. Everything is frozen. We only change the parameters, and you can see that the loss gradually goes down. And I'm showing this so we're not confused, because in the process of this gradient descent, of full batch gradient descent, what we're going to see now, everything is frozen except for the parameters. So we're using all the data all the time, but the parameters are what's changing. So we're going to have to construct this. And here's a reminder about what we call directional derivatives. Okay, so let's say I'm looking at this multivariate function, and I want to look into some direction, and I want to come up with what is the derivative of the curve for me going in this direction. So the way to look at this is I take this sort of 1D function going through this line, and I'm saying, okay, then what is the derivative for this function at this point, right? And this would be this slope that you're seeing there. So we can define it using the regular definition of derivatives, only slightly modified to add the direction. So the direction is added in this, so it's x plus epsilon multiplied by this direction vector v. And then when I divide everything, I also divide by the size of this vector, because I'm only interested in the direction. So I kill the norm. Okay, are we good so far? Everybody with me? Great. And you can easily show that if it's differentiable, this is the same as taking partial derivative according to each dimension separately, okay, multiplied by the size of the direction vector in this dimension. Okay, are we still good? Great. But if you look carefully at what we have here, so you can see that we have here the definition of a dot product between the vector v and this vector with many derivatives. So this is equivalent to doing this. Okay, you see why? Because I just did same index. Okay, we're good. And now we formalized it as this dot product between this sort of normalized direction vector and this other thing. What is the other thing?
Gradient.
Exactly. This is what we call the gradient, right? It's this vector made of all the partial derivatives with respect to all the dimensions, okay, that we have. This is the gradient. And taking one step further, what we get is an inner product between the direction and the gradient. So a directional derivative, if I want to understand what is the slope for me going in this direction, I take the gradient, I'll multiply it by this direction vector, and I get this slope. Good? We're good?
No.
Someone said no. Yeah.
And confusion with we need times gradient. No?
So sorry?
We need times gradient to get me. No.
We need gradient what? Sorry?
Times gradient.
Anti-gradient. Yeah, I'm not talking about minimum yet. All I'm saying is what the directional derivative is. Okay? So this is a directional derivative. Now, here is a few observations. So thinking about the Cauchy-Schwarz theorem, or the Cauchy-Schwarz inequality, whenever you look at a dot product, at an inner product, you can never get higher than the product of the norms. Are we speaking the same language? Are we all okay? Right? You have these two vectors, you take their multiplication, you'll never get better or higher than multiplying their norms. This is the highest you can get. And when do you get this highest? When do you get this to this maximum? when they're the same or rewrite parallel, when they're in the same direction, this is the highest you get, right? Right, because this you can think about it as multiplying the norms and then the cosine of the angle between them, and then when they're together, it's the highest. Question there?
What does define this hypersurface? I mean, the loss function optimization, not optimization methods. What does define this?
What is this?
Yeah. And
This would be the loss. Like the loss as a function of the parameters. Okay? So we know that the maximum we can ever get is the gradient absolute value. And we can also say now that the gradient then directs us to the steepest ascent. So I'm standing somewhere out there in the field, and I want to go as high as possible. The highest place to go is the direction of the gradient. The gradient always points to the highest steep. Okay, and the size of that slope is the absolute value of the gradient vector, like the norm of the gradient vector. Are we good? Doing well? If this was kind of hard for you to follow, you can check it out again later. But I'm repeating, but I'm going to say the conclusion again. Gradient is a vector that always points to the steepest direction. Okay? However, okay, and so the gradient at this point would point about something like this, and at any other point, always takes you up. Okay? The steepest way up. And there is an easy question. We don't want to go up, correct? We want to minimize the loss. Any ideas? What can we use?
9 hinge.
Yes, so just the minus gradient, right? And this is what gradient descent is, sorry, oops. And this is what gradient descent is built upon, taking the minus gradient direction always. So how does it work? Here's our gradient. This is what we want to do. And Augustin Louis Cauchy came up with the algorithm called gradient descent. So you start by random parameters. So it's like they drop you off somewhere in the field, like they used to call in the army. They used to call it like a paratrooper navigation. So you start from a random theta, and then you just repeat until convergence. At every step, you take the minus gradient direction multiplied by this alpha thing you see here, which we call the learning rate, which is the step size. So think about you navigating, trying to find your way. You just take the steps. Maybe it's dark, you don't see anything. You do this with your feet. You feel what's the steepest direction, and then you keep going down, 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 and you're guaranteed to end up in the local minimum. Okay? This is gradient descent. That's all. Now, just to make it practical, so what we discussed is called full batch gradient descent, and this is exactly what we mentioned. And what is the problem here? What can make it impractical? One thing, and this is what you see here. I need to use my entire data set at each step. Okay, you remember why? Because I'm taking the gradient. When I'm taking the gradient, I'm using all the data frozen as if they are like hyperparameters, frozen parameters in a function while optimizing theta. I can't do this. This is too much. This is if I have tons of data. For every step, processing millions of data is impractical. So there is a cool thing called stochastic gradient descent. And this is much, much easier. What I'm doing, instead of taking my entire data at every step, what I'm going to do at every step, I'm going to sample just one instance. I'm going to pick like one email out of the list. And I'm going to use this one email and take the gradient according to it, like using the gradient of the loss, using this one thing. What's the problem here? It's noisy. I don't have the entire true statistics of the dataset. At every step, I have only very small portion of the statistics. But in expectation, it can be proved actually. If you do many steps. At expectation, you're going to end up at the same place as if you did the full batch gradient descent. But this may take long, and this can be like in optimization world, this can be dangerous. You can get to very high numbers and things will collapse and whatever. So there is the golden path, and this is called stochastic mini-batch gradient descent. And I'm sorry for the long term, but you're never going to use it, because from now on, whenever someone says gradient descent, this is what they mean. Nobody means those other things, okay? Everybody is just talking about this. Stochastic mini-batch gradient descent is just gradient descent from now on, and this is how it works. You don't take the entire data set, and you don't just take one example at a time. You take a batch. And if you have billions of examples, the batch can be, I don't know, 64 examples. People like powers of 2. I don't know why. It's not really justified, but they do it. So it can be 64, it can be 256, whatever, 512 at each step. And this is not just a trade-off thing. This is getting the best of both worlds, because you increase the credibility of the statistics you're going to use much more than the memory and time that you pay in order to do this. So having a batch is, think about it like when you do polls before elections. So if I have millions of examples and I only take, I don't know, 512 examples, like 512 examples now, this is a pretty good statistics for these millions. Not perfect, but pretty good, just to take one step. Okay? And here's an example. So in blue, you see the full batch gradient descent. I don't know, it says batch gradient descent, it's full batch gradient descent. And this is very, very accurate. You always go in the direction that you need to go. But what you can see in this picture is that every such step takes a long time of computation. Probably depends on how much data you have. Okay, so this is the best thing if you have no problem processing all the data all the time. You keep taking pictures. We will upload this, and this is also available like in the website from previous years. Okay, but if you want to take pictures, you're invited. Yeah.
Where is the noise coming from?
Sure. So the noise. So let's look at the stochastic gradient descent, like this horrible purple path. And the noise is coming from, because when I take just one example out of the data, I don't really see this entire curve thing. I don't really see it. All I see is a glimpse of one example that represents the data. And I also suffer the noise when taking a batch from the data. It's like the surface changes, the function changes, because what you optimize are the parameters theta. But all the frozen parts of the function are actually, it's the data. It's like x multiplies theta. So think of a function with those hyperparameters multiplying the things you want to optimize, but you're not getting all of it. You're getting a function that is almost that or close to it because I removed some parts of it. And at every step, the function changes. So if you want to have like a metaphor for it, so whenever you do stochastic gradient descent, whether it's stochastic batch gradient descent or just a single example at a time, it's like having an earthquake. So we talked about this navigation thing. So it's like having an earthquake, and the smaller the batch, the worse the earthquake is, and you keep going. So at expectation, you're still going to get to the same place, but the surface keeps moving from one step to another. Yes.
So there is some implicit assumption that the function you're looking for doesn't describe the data set perfectly.
It's not just an assumption. It describes, like, the full batch gradient descent. This describes the data set perfectly. I'm not saying it's describing real life, because the data set is a sample from like real life, there is a test set, right? That I want to generalize to. But for the data set, full batch gradient descent is perfect. Okay? Are we good with all these optimization methods? So what we're going to be using always is stochastic mini batch gradient descent. It looks like this, you see, so slightly more steps than this one, but think about this one step needs maybe, I don't know, million examples, billion, I don't know, depends on what you're doing. And this may be like 64 examples. So this is a very good price to pay, like to do like maybe 3 times the amount of steps or 2 times the amount of steps Okay, but every step is like a million times cheaper. Okay, now let's try to apply this specifically for linear regression. So for linear regression, here's the loss function, right? We have this MSE, so we sum the squares of all the differences between the predicted, which is theta transpose x. And so to do gradient descent, we need to take the gradient for this. We have to take the derivative. So let's take the derivative with respect to theta. And if you are uncomfortable with taking derivatives with respect to vectors, then you can later do it like slowly and see what it exactly means. But mostly it's the same as taking the derivative with respect to scalars. Okay, so to take the derivative, okay, so the first step, so it's pretty easy, right? It's like we have this in squares, so you know, like you have x squared, so the derivative is 2x. So the two that used to be here, and we multiply by this x again, and now we can look at this like in a more matrix way. So think about this entire bracket as this vector, because it is a vector, it's that theta multiplied by a vector minus a scalar. So what I'm going to do now, I put this index here, and now again this thing looks like a dot product. So it's an inner product between the matrix X and this X theta minus Y. So this is what I end up as the gradient. Okay, are we good? So this is the gradient, and note that we got here this thing that earlier we called it the error vector. So this is why we can say that gradient descent for linear regression can be compactly formalized this nice way. You just at each step you take theta, and then you reduce. Alpha is the learning rate. It's a hyperparameter. It's usually would be like 0.001, whatever. Okay, divided by the number of instances in the data set, and multiplied by this x times x matrix times the error vector at each step. Okay, this keeps updating. Okay, quick question. Let's see if you can observe this one. Can you find a relation between the convergence, when this thing converges, and the normal equations that we discussed before? Think more about the intuition. Anyone? Yeah.
So when you're near convergence, X transpose E is going to be close to 0.
Exactly. Yeah, that's true. So when this thing converges, so I get to a steady state, this is not going to change anymore. And the only way this is not going to change anymore is if this part is 0. This part is 0 means this part is 0. If this part is 0, it goes back to what we've seen before, that the error, remember this vector, is now perpendicular to the subspace, the span of the matrix X. Okay, cool, right? We got this from two directions. Okay. Okay. So by now we know what gradient descent is, and we know how to apply it specifically to linear regression. We have this nice closed form. Now we need to advance ourselves and to start looking and thinking about things that are not going to be linear anymore. How do we use what we have so far? How can we apply it to more advanced hypothesis classes? So the linear part is important. It's not like we learn about the linear part, now let's learn about non-linear part. We're going to leverage it, and let's see how this goes. This goes through this thing we call feature transform. So here's a quantitative. This is a classification problem that I want to solve. I only know linear. Okay, you're going to learn about linear classification too in the tutorial this week. I only know how to do linear classification. What can I do? So there is something very obvious here. Like if I had another way of looking at this data, I would be able to use the tools that I have to classify this. Sorry?
Polar coordinates.
Polar coordinates is a very good direction, okay? but I'm asking about like more in general. So so the thing, okay, polar coordinates means if only instead of looking at x and y, I would look at the radius and the angle, whatever. Okay, this would become easy, right? Even solving it by hand, I would say, okay, everything in radius bigger than whatever is blue star, and everything smaller than this that has radius smaller is red circle. However, when I get the data, it's going to be a list of x and y's. So what I can do is do this transform. So, for example, in this case, all I need is the radius. So I just come up with a new coordinate, with a new measure. I call this z. In this, it would be better as r, right? I don't know why I call it z. So, and z is going to be the square root of x squared plus y squared. And then I put the data again. But now I have this, for this example, x coordinate and z coordinate instead of x and y. And look at this. Looking at the same data with different coordinates achieves a way to classify things linearly that I was not able to do before because it wasn't linearly separable. Are we good? Are we okay? Any physicists here? Few. So you should be, this should kind of sound familiar to you because this is sort of what's happening. So in the presence of mass, in general relativity, in the presence of mass, we have a different metric for the space. So in particular, the Schwarzschild metric, it says that we had these geodesic lines. We're still walking in straight lines, but we're using a different metric. So think about it. This is a different metric, different coordinates, depicting the same thing we had here. We came up with a hypothesis. Here it is. And then when we map it back, this hypothesis is actually this circle. If we do this inverse feature transformation. Okay? And usually what we would bump into is adding more features so that things are linearly separable. So think about this very non-separable, non-linearly separable thing. I can remap it, and I don't care. I used to have 2 dimensions, but now I have 3. In these 3 dimensions, I can use this subspace division, and this is just linear classification that's working. And I don't care anymore. But if I do care, like for analysis sake, I can remap this thing, do the inverse. Sometimes it's not well defined, but if I can, then it would be mapped to this very, very non-linear classification that you see there. So this is cool. Linear on another metric, on other features, on feature transform, can be non-linear on original features. And this is a very practical thing that is exactly what we're going to do and what we're going to deal with. So the idea is you have some input, you do some feature transform, just as we did now. So we had this z equals the square root of x squared plus y squared. Then you apply a linear hypothesis. And this whole thing together is a non-linear hypothesis. Okay, are we good? Great. So an example, a very cool example, is just polynomial regression. What do? We just had, let's say we just had a scalar. I want to fit a polynomial to data. Okay? I make up new features. What do I care? Okay? So the new feature, instead of, I used to just have x. That's it, a scalar. The new features are going to be x0 is going to be 1. Then x1 is going to be x. I had these already. Okay? But now I'm going to make up many more dimensions. And these are just going to be x2 is going to be x squared, and x3 is going to be x quadratic, and so on. And then I just do linear regression over this x squared whatever, and this fits a polynomial to this. Okay. How much time do we have? Just what we need. Okay. So, last thing we'll discuss today, and then I'll show you a quick thing. Okay? And this might be the most important slide to see in the world of machine learning. Okay? And this is understanding the error when we do prediction, because this is understanding what we're seeing when we're trying to optimize some system to do something and we're not getting what we wanted. What is it made of? Okay? So think about the test loss. I just got an email, a new email, and I classified it. So I said, this should be like 80% spam. Whether I'm right or wrong, and to what extent I am right or wrong, is called the test loss. Are we good right now? I want to see what it's made of. So I would want a zero loss. Like I'm getting 10,000 new emails that I haven't seen before, and I'm saying 100% the right label for each one of them. This is what I would want. Unfortunately, I'm not going to get it. I'm going to get something else. And the way it's going to be constructed is as follows. So the first thing we need to notice is that life is random. So for example, let's say I have a system and I'm trying to predict whether or not there's going to be a car accident. Life is random. There's no 100%. There is no model that is going to be right 100% of the time. Everybody's agreed? Think about the stock market, whatever. Okay? But the best possible that I can do, taking into account the stochasticity of real life, is what we sometimes refer to as the base optimal predictor. And this is the best possible H, the best possible hypothesis you can have, not limited by anything. Okay? So we have this first gap because of the randomness. We have nothing to do about this gap. This is the H base, is the best model in the world that even theoretically someone can achieve, unless you get more data. Okay? Great. But then we're still going to have a lot of trouble. So the next thing is that we have this hypothesis class, and it's limited. So I'm going to use even if I can find the best hypothesis in the hypothesis class, the hypothesis class doesn't necessarily perfectly maps the x's to the y's. And this is called underfitting. A very good example of it is, what if the true mapping is nonlinear, is whatever, polynomial, and I'm using the linear hypothesis class, like you see here, is going to be underfitting. I'm using something that is not complex enough, not complicated enough, in order to characterize the mapping that is ideal. Good by now? Okay, okay. Stop me if you miss something. Okay. Then we're going to come up with maybe the most famous type of error, and this is called overfitting. Overfitting means that we could come up with the best hypothesis to best map the training set and to get the predictions for the training set. It means we got zero loss on the training set, but not the test loss. And here we have this generalization gap. Overfitting means that I'm good on the data set, but I'm not good in real life. This can be because of some reasons. We're going to discuss it more thoroughly in a second. Okay? And this would typically look something like this. So I have this very good mapping, a lot of parameters, whatever. Okay? This is not underfitting anymore. And I match the training set very well. The orange is the training set, but not to the test set. Usually I went too complicated. Okay? And then there is the last thing is the optimization gap. Say, underfitting fine, overfitting fine, I have exactly what I need, but I'm going to use some algorithm to try to find the best hypothesis in the hypothesis class. Not necessarily I'm going to be able to do this. Okay, because optimization is a hard problem. Think about gradient descent. What if the step size is too high, and then you see this, you sort of jump from one to another, from one side to another in gradient descent, and you can't get to the real minimum point. Okay, optimization is not perfect. And so these are the three things you can do something about, and they're super important when you analyze what you do. Whenever you get an error, whenever you train a model, you want to get something, you're not happy, you go here and you ask yourself, is it underfitting, overfitting, or optimization? This is the most important thing you need to do in the process of training neural networks. Yes. Yeah.
Is the optimization gap always over the overfitting gap, or is it?
No, it can be any of them. It can be any, and usually they will be all together. The question would, you have all of them. I assure you this. The question is, which one is going to be the most significant, and that you can most easily do something about. Okay, just a few less words about overfitting. So one paradigm to look at it is, if my model is too complex, I have too many parameters, I can map things too crazily, then the training error will go and drop, because I'm going to be able to map the training set very, very good. But then I'm not going to generalize very well. I'm going to look, not to look at simple rules, but very complicated rules that match specifically only to the way the data set was sampled and what I got. I'll show you examples in a second. And I know this is not very intuitive. What do you mean? You're too good at fitting and then it's bad. I'm going to show you example with polynomials in a second. But here is like metaphoric examples. So what if, so this is how data can influence. So if I want to match someone the exact bed, and I take one night, say let's map the way you were sleeping, and I say, oh, this is the perfect mattress for you. Okay. Of course, this is a very bad idea because it doesn't generalize. It's not going to generalize to the next night. Here's another fun example. So if you look at this matrix, and then that matrix, and you say this is the x and this is the y, this is the label. This can be, this is a squared, but it's also this funny thing of taking like doubling this digit. Okay, and you can't really know what the rule is. There is a simple rule. Usually you would want the simplest rule that best fits your data. But sometimes you would even want a simpler rule, even if it fits your data not as well. You would need to prefer some simplicity on fitting to your data set. I'm going to show you what it looks like. I think this shows it the best. So let's say I have this true function. This is a third degree polynomial. Okay, so it's like x what, okay, x to the power 3, but with some noise, as in reality. And so this is the true data that I have. This is like test data, the real data of life. Are we good so far? Now out of this, I sample IID. Okay, I sample a training set, which is these orange dots. And I want to train this in order to predict, this is regression, to predict values for the test set. Are we good by now? Now I'm going to use this polynomial regression that we just mentioned a few minutes ago. Okay? So if I set the degree to 0, so think about this, only one parameter. Okay, it's like just theta 0. Polynomial of 0 degree is going to be, take it as an extra homework. It's very super easy to see. It's going to be the mean label, but averaging the label. So this is what I'm going to get. And you can see above, there is the train error and the test error, okay? And on the left side, the left-hand side, there are going to be plots of them with respect to the degree. This is going to be the degree of the polynomial that we're going to use, and this is the loss in logarithmic scale. Okay, now going to first degree polynomial. So this is first degree is linear, so this is just plain old linear regression, right? And you can see the train error dropped with respect to the just 0 degree, and also the test error. I'm going to degree 2. So it kind of still looks linear, but this is the side of a parabola. Now I'm going to degree 3 and look at the train and test. But I'm going to go more to degree 4 and 5 and 6. And look at what's starting to happen. So the train loss is always reducing. It always goes down. There is no reason in the world why the train loss would not go down when I just add more parameters. If they're not useful, they can be 0 or whatever, right? Okay, the train loss keeps going down, but the test loss is now starting to rise up. It's starting to rise up, you see? So right now, I'm getting to this realm of what we call overfitting. And as I keep going, this is getting really, really crazy. and you look at the curve is starting to do really impressive job at fitting all the data set points. Okay, it's almost a perfect fit. So you can see that the train error is many zero point many zeros than 1. Okay, and the test error became huge. This is logarithmic scale. The test error became huge. Okay, and as I keep going, this keeps happening. And you can see the best test loss, this is interesting, that I got was around here when the degree was 3, which is the true, remember the ground truth thing? The true degree of the polynomial that we were using. But unfortunately, in real life, I don't know like what is the ground truth. But what I'm saying, this is a way to understand overfitting. I got many parameters. I get like a huge degree polynomial, and I used it. And what happened was I got addicted to the training set. I wanted so much to fit it, and the price I paid was that with the simplicity. And then I was not able to generalize anymore and to be able to fit to the test set. So this was just fitting. This was more influenced by the stochasticity of sampling the data set out of the true data, out of the test set, rather than being able to generalize. So this is overfitting. We're done for today. I'll just say that you have this tutorial this week, and it's going to be about linear classification method and some very basic PyTorch. You have the homework number 1 on the website already. You can go ahead and start. There's like the theory part, you can already do it. And then for the coding part there, you probably better start after the tutorials, so you get some basic PyTorch, and this will be with Leo Yaviv. And then next week, unfortunately, it's going to be me again for you guys, and we're going to start exactly this point. Remember the feature transform? Remember this one. This is the starting point from next week, and this is where neural networks start. Okay? I want to thank you. I had a really great time teaching you today, and I'll see you all next week.